Imagine you're cruising at 30,000 feet inside this massive metal tube, right? It weighs hundreds of thousands of pounds. And to actually move the heavy flight surfaces against those ferocious, high-speed winds outside, well, it requires a level of mechanical force that human muscles literally just cannot produce. So how does the aircraft actually pull this off? Welcome to The Explainer. Today, we're taking a fascinating journey straight through the hidden bloodstream of an aircraft, the hydraulic system. It's this completely invisible world of immense pressure, really clever engineering, and, as you'll see, some microscopic dangers.
Here's our roadmap for today's journey. We'll start with the aircraft's hydraulic heart, then move on to how we store power in the reservoir. After that, we'll look at a hidden danger called cavitation, how we drive the system with pumps, and finally, how we keep all those fluids clean and cool. Let's get right into it. Section 1. The aircraft's hydraulic heart. Okay, let's dive into this overarching system. This is the absolute core infrastructure doing all the heavy lifting required to fly and safely maneuver these massive commercial machines. What we're looking at maps out the complete closed loop of the hydraulic fluid. You really got to think of this fluid as the aircraft's literal lifeblood. It starts its journey securely housed in the reservoir, gets drawn out and heavily pressurized by the engine-driven hydraulic pump, and then travels out to do the actual physical work at the actuator. You know, things like dropping the landing gear or moving a wing flap. And then it makes its way right back. On that return trip, it passes through crucial filters and a heat exchanger before finally resting back in the reservoir. It's just a brilliant, continuous cycle of transferring power.
Moving on to Section 2. Storing power, the reservoir. So our fluid's journey begins right here in the reservoir. This is the starting point, basically the storage vault. Its primary job is just to ensure the system always has a steady supply of fluid under literally all operating conditions. But it also acts as a buffer. It makes up for any tiny leaks, gives the hardworking fluid a place to cool off, and allows for thermal expansion. But here's the thing, not all reservoirs are built the same, because not all flight conditions are the same. On the one hand, we have non-pressurized reservoirs. These just rely on standard atmospheric pressure to deliver oil to the pump, which, works perfectly fine for aircraft operating at low altitudes or during really calm, non-violent flights. But on the other hand, we have pressurized reservoirs. When an aircraft is operating up at extreme high altitudes where atmospheric pressure just drops off a cliff, or it's executing violent flight maneuvers, standard gravity and air pressure just aren't going to cut it. We actually have to artificially pressurize the tank to ensure a positive flow of fluid to the pump, and crucially, to prevent the fluid from foaming up. So you might be wondering, how do engineers actually force this fluid out of the reservoir at those crazy high altitudes? Well, they primarily use two pretty ingenious methods. The first is hydraulic pressurization. This is where pump pressure is applied to a small movable piston, which is then attached to a much larger piston that literally forces the pressurized fluid into the pump inlet. Pretty clever, right? The second method is air pressurization. This actually taps into the aircraft's own engine bleed air or pneumatic system air to press down on the reservoir's contents. These forced pressures are an absolute necessity. Without them, you'd get dangerous air pockets forming in the lines, and we definitely do not want that. Now, what's really interesting here is looking inside the actual hardware of a hydraulic reservoir. Notice those elements jutting out from the sides? Those are baffles and fins. And they aren't just there for structural support. No way. They have a vital, physical job to do. They actively stop the fluid from randomly swirling and surging around inside the tank when the plane makes a sharp turn. Think about it. Without these fins, the fluid would violently whip into a foam, allowing air to mix in and enter the pump. And as we're about to see, that is an incredibly dangerous scenario. Which brings us to Section 3, the hidden danger, cavitation. We're now transitioning from the safe, controlled storage of the reservoir right into the volatile, low-pressure environment of the pump inlet. And I want to pose this really high-stakes question to you. What actually happens when the pressure drops too low inside the pump? I mean, it sounds like a purely theoretical physics question on an engineering exam, right? But at cruising altitude, the answer to this question represents a massive threat to the aircraft's survival. Let's do a step-by-step breakdown of how a microscopic physical anomaly turns into a literal chain reaction of destruction known as cavitation. Remember, the pump doesn't actually draw the oil in. Atmospheric pressure delivers it. So step 1, the local pressure on the inlet side of the pump drops way too low. Because of this, we move to step 2. Air is literally drawn straight out of the oil itself, forming bubbles. Step 3, these harmless-looking bubbles get swept right into the pump and are rapidly compressed in the high-pressure region at the pump's outlet. And finally, step 4. Under that immense pressure, the bubbles violently collapse. Let me really emphasize the massive stakes of this process by reading a direct quote from our source material. It says, this collapse will cause localized shock waves to impact the subcomponent surface within the pump, resulting in pump failure. Just think about that for a second. We aren't talking about a massive external explosion here. We are talking about microscopic air bubbles, little bubbles possessing the sudden, violent force required to completely shatter and destroy solid metal pump components mid-flight. It's wild. Moving right along to Section 4, driving the system. Pumps. To ensure that fluid keeps moving powerfully and safely without cavitating, we rely on the mechanical heart of the aircraft. One of the primary drivers of this system is the constant displacement pump. By definition, this kind of pump supplies an absolutely fixed quantity of fluid during each and every revolution, completely regardless of whether the system actually needs that pressure at the moment. So the crucial point is, because this pump relentlessly pushes the exact same amount of fluid no matter what, the system absolutely requires a pressure regulator or an unloading valve. Because without one, the pump would literally just keep building and building pressure until the pipes completely burst. Now, because losing hydraulic pressure basically means losing control of the aircraft's control surfaces, redundancy is everything in aviation. Everything. So here's a quick list of the 4 distinct energy sources that can drive these hydraulic pumps. Primarily, they're aircraft engine-driven. That's the main way. But in an emergency, we have the ram air turbine. That's a small propeller that drops right down into the windstream. There are also hand pumps for manual override and electric pumps. This stacked, multi-layered redundancy ensures the hydraulic system never ever loses its heartbeat. And finally, Section 5, keeping fluids clean and cool. Let's move to the final stage of our fluids journey and see how this builds before it rests and starts the whole loop all over again. 2 unsung heroes of the aircraft are the return filter and the fuel and hydraulic oil heat exchanger, and this brilliantly illustrates the sheer elegance of aviation design. Before the exhausted, hot fluid returns to the reservoir, the filter meticulously strips out any dangerous contamination. We're talking about tiny metal shavings that could cause wear or even spur that terrifying cavitation we just talked about. Meanwhile, the heat exchanger actively cools down the boiling hot hydraulic fluid, and here is the absolute genius part. It cools the hydraulic fluid by transferring that excess heat directly into the aircraft's cold aviation fuel right before the fuel enters the combustion chamber. It is a completely self-sustaining, utterly brilliant exchange of energy. Which brings us to our final thought for this explainer. If a microscopic air bubble collapsing under pressure has enough violent force to destroy solid metal and cripple an aircraft's hydraulic pump, how meticulous must aviation engineering be to keep you safe? Every fin in the reservoir, every pressure seal, every filter we've looked at today is part of a perfectly choreographed dance of physics and mechanics. And it's all happening invisibly, just beneath the floorboards on every single flight you take. Thank you so much for joining me to explore this incredible system, and keep an eye out for our next deep dive.